Right, welcome back, and we're continuing talking about chemical change, and now we're going to look at how atoms combine, atomic combinations. We said earlier on in lesson 15 that atoms bond with each other to attain chemical stability. And we have got three types of bonding. We've got what we call covalent bonds, ionic bonding, and we also have metallic bonding. Now, covalent bonding occurs when there is sharing of the bonding electrons, okay? A pure covalent bond is formed when there is equal sharing of bonding electrons, and this occurs between atoms of the same element, such as the formation of the hydrogen molecule, the diatomic molecule H2O, or oxygen O2, or you would think of the chlorines, the bromine, those ones. There we have got equal sharing of the bonding electrons, and therefore we are having what we call pure covalent bonds. Okay, now we can also have what we call polar covalent bond. This is formed when the bonding electrons are shared unequally. One of the bonding atoms tends to attract the bonding electrons more towards itself. And in this case, this ability to attract the bonding electrons towards an atom, okay, the ability of an atom to attract bonding electron pair towards itself is called electronegativity. And if you look at your periodic table, you will see those numbers 2.0, 2.1, whatever, those ones, those are electronegativity values, and those tell us how much an atom is going to attract the bonding electrons between itself and other atoms. Okay. Now, there's Lewis diagrams that we use to show valence electrons. And what are valence electrons? Valence electrons are electrons found in the outermost energy level in an atom. And these valence electrons obviously are the ones that are involved in chemical bonding. So valence electrons are of interest to scientists because those are the electrons that make things happen. Those are the electrons that are involved in chemical bonding. So we can't study chemical change or atomic combinations without looking at what happens to the valence electrons. Now, Lewis diagrams are used to show valence electrons and how they are involved in bonding. Now, let's have a look at this. Lewis diagrams, how do we do them? If you look at nitrogen, for example, nitrogen is element number 7, and it is in group 5. And because it is in group 5, it means it will have 5 valence electrons. So this is how you will do it for nitrogen, your Lewis diagram. So these dots here represent electrons. So you will see I started there, came down here, came down there, and I'm there. From there, once I have 4 of them all around the atom, single electrons, I would start pairing them. Okay, now it's 5 valence electrons, so I must have 1, 2, 3, 4, 5. This is called a lone pair. That's when you have got a pair of electrons that are from the same atom in that way. Now you would see there are 3 electrons that are single. In other words, they are occupying their orbitals, these valence electrons, alone in those orbitals. They are not paired up. And those are the those are the electrons that are going to be involved in chemical bonding. So this tells you immediately that when we look at nitrogen, we should expect it to form 3 bonds. Now, in a nitrogen molecule, this is what would happen. Let me use crosses to show that these electrons are for the other nitrogen atom. So these two will share to form a bond. Those will share, and these ones will also share. And in that way, you would have formed a triple bond between the nitrogen atoms to form your N2. Now, when you use lines to show the bonding electrons, we now talk of the Cooper notation. You must have heard of this, and if not, obviously your teacher is still going to talk to you about it. Okay, you can go ahead on your own and try to show how the chlorine molecule is formed, oxygen, and the carbon dioxide molecule there, in showing how the bonds are being formed, making use of Lewis diagrams like I did with the nitrogen. Okay, oxidation numbers. Free elements have 0 oxidation numbers. Okay, and oxidation number of an ion should equal the charge on it. In other words, if I'm talking about an ion of sodium, it means the oxidation number of sodium here is +1. Okay, sodium ion. Okay, and oxidation number of oxygen is always given as -2. Oxidation number of hydrogen is +1. And therefore, if we know all this, oxidation numbers of halogens is -1. If we know all this, we'll be able to calculate what oxidation number of certain atoms in a compound or in a molecule is. That brings us to the end of this part here. Let's meet in the next section where we will elaborate further on some atomic combinations.